So welcome to today's Postgres conference webinar, Blockchain as a Database. We're joined by Abdullah Uz Tansel, Professor of Computer Information Systems at the Zicklin School of Business at Baruch College and Computer Science PhD program at the Graduate Center. In today's talk, we'll formalize the blockchains as a database and explore how blockchain concepts can be incorporated into traditional and relational databases, both in general and to PostgreSQL in particular. My name is Lindsay Hooper. I'm one of the Postgres conference organizers, and I'll be your moderator for this webinar. A little bit about your speaker. Professor Tansel is Professor of Computer Information Systems, and his research interests are database management systems, temporal databases, data mining, and semantic web. Dr. Tansel has published many articles in the conferences and journals of ACM and IEEE, and he has a pending patent application on semantic web. Currently, he's researching temporality and RDF and OWL, which are semantic web languages. Dr. Tansel served in program committees of many conferences and headed the editorial board that published the first book on temporal databases in 1993. He's also one of the editors of the forthcoming book titled Recommendation and Search and Social Network, to be published by Springer. With that, I'm going to hand it off to Dr. Tansel. Take it away.
Thanks, Lindsay. Good afternoon, everybody, or good morning, or good evening, wherever you are. I'll be talking today about databases and blockchain, a very timely topic. The talk, we will start with a brief introduction, and then I will cover blockchain fundamentals, then talk about the databases, and finally see how we can combine these two. And then we will wrap it up. There will be a bunch of terminology like consensus, ledger, trust, I will be using during the talk. I'm sure you are familiar with them. I just wanted to give you a list of these terms that are very common in blockchain space. In explaining the topic, I will start first with the Bitcoin ecosystem and explain what the blockchain is before talking about databases. I'm sure most of you are familiar with these topics. However, it would be a good time in the talk to review them. First, in the blockchain environment, it's no different than the real life we live. There are a bunch of actors. No one trusts each other, and each is free to do whatever he or she wants, including stealing. Some also may want to hack or disrupt the system. And moreover, there is no need to be identified or documented or approved by anyone. So the Bitcoin ecosystem aligns the incentives of these actors to create a working, growing, and indestructible ledger that remains open and transparent to all. In short, it is a decentralized, autonomous organization. Bitcoin ecosystem works on a peer-to-peer network, and the peer-to-peer network is dynamic. Here in this sample diagram, we see a bunch of nodes that are connected and that are peers to one another. And the nodes, they all agree to follow the same principles and keep the ledger. In other words, consensus. And then within the principles, they can act freely. Of course, there may be the honest nodes acting honestly, and there may be also non-malicious nodes because of software bugs, hardware failures, power failures, etc. And there may be malicious nodes as well, knowingly trying to game the system or misbehaving. So in this system, all the data is recorded in the blockchain. I'm sorry. So blockchain, in this respect, is a record-keeping system. Actually, the databases are also a record-keeping system. The blockchain is made up of blocks, and the block has a header and also the body. The body of the block carries the block's payload, a bunch of transactions. Usually, they are organized into a Merkle tree. And the block header has identifying and verifying data about the block, like the hash of the previous block, the hash of the current block, the nonce that is used to create or to prove this block, and also the root of the hash of the root of the Merkle tree, etc. So these blocks are chained together in a linear fashion to form the record-keeping ledger that is called blockchain. In Bitcoin environment, the original block was created by Satoshi Nakamoto, that's the Genesis block manually, and then the system, as it evolved, added the other blocks over time. So the blockchain over time grows. Let's see what happens. A node, which is called a miner, adds a node. The miner first solves a cryptographic puzzle to get the permission or the capacity to add the block. This process is verifiable, and therefore everybody can verify whether the miner is honest or not. In every 10 minutes, a new block is added. The mining process works through a concept called proof of work, and there are other mechanisms like proof of stake, etc., that are being explored widely as well. So the miner A, let's say, successfully solve the cryptographic puzzle or win the lottery by solving the puzzle, and has the capacity to add a new block. So the new block is added here, let's say at 9 a.m. Now, in 10 minutes, another miner, let's say B, solves the puzzle and wants to add the new block, which is shown as the brown block here. Either because the miner chooses to do so, or because of the latency and delays in the peer-to-peer network, the miner may decide to add the block at any one of the previous nodes in the blockchain. And let's say the miner decides to add it after this block. In this case, the blockchain has forked because it's evolving in two branches. The succeeding miners may prefer to go with the brown tip or with the other tip. In the end, the longest chain becomes the consensus blockchain that everybody agrees on. Here, I'm not going to talk about the details of the mining or how it is done, but essentially, this is the process how the Bitcoin blockchain is formed. So in this process, we see the following building blocks. One, first, there is a consensus building block that is an agreement mechanism on the current state of the world, I mean the Bitcoin world. The second component is how that consensus is achieved, that is through mining. Mining is the method or the protocol that incentivize actors to facilitate the consensus and add blocks to the ledger. And finally, the third one is a data structure or a database for holding the blocks and making it tamper-proof and easily verifiable. Additionally, there is an application API and there is a propagation module. However, these are not, for our purposes, are not crucial. For the blockchain purposes, consensus mining and data structure are the essential blocks. So in the consensus, as I mentioned, there are various methods. Bitcoin consensus mechanism is based on proof of work, and it's called Nakamoto consensus. And there are other methods like proof of stake, proof of authority, which are based on the sophisticated algorithms like Byzantine fault tolerance, etc. And that's also white space extensively being explored. So the consensus protocol should have the capability of being liveness. That means every non-faulty node decides on the transaction in finite time. Safety, all transactions get recorded in the blockchain. And consistency, eventually every node has the same copy of the ledger. In a nutshell, as I mentioned, in Bitcoin, the consensus is called Nakamoto consensus, and this is facilitated by mining. And mining actually is solving a cryptographic puzzle. We can also look at it as a kind of lottery system. Whoever solves the cryptographic puzzle wins the lottery and hence adds the block to the blockchain. In blockchain environment, there are three fundamental considerations or parameters, I would say. One of them is scalability. By the scalability, we mean the capacity of the blockchain system to to process more transactions and also to increase its storage capability when needed. In fact, in Bitcoin blockchain environment, a block is added in every 10 minutes, and the number of transactions processed is about 6 transactions in a second. When we consider real life payment systems like Visa or MasterCard, they are capable of processing thousands of transactions in a second. The other aspect is the decentralization. Whether the system is public and totally decentralized, and there is no central control, or there is no owner, and also joining the system could be permissionless, means open to anyone. The third aspect is the security of the system, whether the system works correctly in processing the transactions, and the system is free from hacks and unintended interferences. Having all these three capabilities in a blockchain environment, in a Bitcoin blockchain environment, is at the moment impossible. Achieving these three properties, two of them can be achieved, but the third one is very problematic. There are research efforts in solving this. However, it is a real challenge. As I mentioned, Bitcoin blockchain environment prioritize decentralization and security over scalability. There are different types of blockchains, and we can classify them with respect to the participants in the system. The participants may be called validators, miners, etc. They are handling the tasks of the system. So the first property is permissionless versus permission blockchains. That means the validators or miners can join the system without any permission on their own prerogatives. For instance, Bitcoin environment, it is permissionless, and anybody who has the hardware and software can join the system. Also, the validators and miners can be untrusted, anonymous, or trusted, known. Again, in the Bitcoin environment, they are anonymous, and therefore they are untrusted. Please don't misunderstand me when I say untrusted. That means there is no assumption. They may behave in a trustworthy manner or untrustworthy manner. So along these properties, there are two main types of blockchains. One is public blockchain, and that is the Bitcoin blockchain system. The second one is consortium or federated blockchains. We know the properties of public blockchains. I talked about them in the last several minutes. On the other hand, the consortium or federated blockchains are permission blockchains, and the nodes, the validators, are known in advance. They can be trusted or untrusted. That depends upon the protocol, consensus protocol they are following. Many of the enterprise applications are today based on consortium or federated blockchains. In this case, a bunch of organizations come together, or one organization leads and they form a consortium to have a blockchain. You know many examples. One good example is Facebook's Libra blockchain, I would say. The private blockchains is a blockchain within an enterprise. It's private, it's not open to other organizations or public. Before I proceed to the databases, I want to quickly review Hyperledger Fabric, which is a well-known product by IBM for consortium blockchains. I'm sure you heard about Hyperledger. Hyperledger is an open source suite of systems handled by W3 organization. And Hyperledger Fabric is the one IBM is developing. And in fact, it's commonly used in the enterprise blockchain environment. And I can say that it's a fairly good representation of many of the consortium type blockchain systems. On the right-hand side, you see the transactions, like transaction the T1, S1, etc. It's a block. and then there is another block, and they are chained. That is the blockchain. In this peer-to-peer network, there are nodes, and each node has a different functionality, and some nodes may have more than one functionality. As you see, the green nodes are called peer nodes or endorsing nodes. And in the center, you see green nodes. Those are called orderers. So, as I mentioned, organizations join in the consortium blockchain. So an organization may have several peer nodes, several endorsing nodes, and may even have the ordering node. And of course, each organization has also capacity to get the cryptographic credentials for the nodes and for the users. So a user that is connected to a peer node submits or connected to an endorsing node submits a transaction. Either the peer node passes to the endorsing node or endorsing node directly submitted to the endorsing node. Then these transactions are passed to the orderers, and then orderer nodes order them into blocks, and then each peer finally records it in its own ledger. That is what we see in the second slide. Here is the sequence of operations I have just explained in the previous transparency. If I repeat it again, so a transaction is submitted to an endorsing peer. What the endorsing peer does is to simulate the execution of this transaction. The transaction is executed or simulated by the endorsing peer to verify that it works correctly. And then the transaction, for the transaction, it creates a read-write set. And then that is provided back to the client, and the client sends it to the ordering nodes. The ordering nodes receives the transactions, applies the consensus protocol, and then creates a block. Various consensus protocols can be used here. For instance, in the earlier versions of the Hyperledger fabric, Kafka, the Zookeeper, is the consensus algorithm, or a Byzantine fault-tolerant algorithm is also used. Then the ordering nodes, once form the consensus and form the blocks are passed to the peer nodes, and they are committed into the blockchain, and the blockchain is growing. Here, there is a way, there is a database to keep the blockchain. Any key value store commonly used, and recently MongoDB or LevelDB are being used in as the database. Similarly, for the blockchain, to Bitcoin blockchain, the LevelDB is used to store the blocks of the blockchain. So essentially, this is how a consortium works. Of course, there are many others like R3, Corda, etc. They work in a similar fashion. They are not exactly alike, but the idea seems to me essentially the same. Before we talked about the databases. What are the properties of the Bitcoin blockchain environment or any blockchain environment? So Bitcoin blockchain environment solves the double spending problem. Once the data is digitized, making it unique is extremely difficult. Therefore, in the Bitcoin environment, by copying and pasting, the transactions can be submitted to the system several times. However, Bitcoin blockchain does not allow it. Also, decentralization. Bitcoin blockchain is completely decentralized, and the consortium database systems are somewhat decentralized. It's also immutable, means that once data is recorded in the blockchain, it cannot be changed. Therefore, it is tamper resistant as well. Non-repudiability of the transactions. Once you commit a transaction, you cannot reject it. Finality, that the transactions processed are final, and also provenance, the history of transactions are available. There is no single point of failure and control, and it's also public, and it is censorship resistant. Anybody can join it. Nobody can leave you out. And of course, they are capable of carrying out smart contracts, and also owner-controlled assets are available. Now, let's look at the, the databases. The databases provides us as a record-keeping system, low latency. That means fast transaction processing and high transaction capacity, and also data modeling and rich querying that is facilitated by indexing in a fast manner. And the databases scales up to a point well, depending upon their architecture. And also, it's a mature software environment. There are products, database systems that have been developed and used for a long time. Also, the privacy is guaranteed or maintained in the database environment. There are utility tools like recovery, backup, etc. So essentially, what the blockchain environments provide and what the databases provide are two, I would say, desirable set of properties. Whether they can be combined or not, that's a good question to explore. Now, even though I have delayed the definition of what a database is, after quickly reviewing the Bitcoin blockchain, now we can define what a database is. A database is a structured set of data. In other words, it is a record-keeping system. The data, the transactions and other activities are recorded in the database. In having a database, there are three fundamental questions that need to be addressed. First, who owns the database and who maintains the database? So as part of maintaining, who has the capacity to write the database? And the third question, who can retrieve from the database or who can join the database environment? I have been in the database space for a long time, over several decades. And these questions were our basic assumptions, and we never questioned them. They were given to us, and we were trying to create the best database that is possible. So typically, the database has an owner. In this case, the bank is owner. The bank is handling our accounts, and bank allows us to use it. And when I use an ATM system to withdraw money, my transaction is processed by the bank on my behalf, and the bank's proxy in the database system, the procedure, writes my new balance into the database. The problems like double spend problem does not exist here because the bank does not allow it, and other problems like security, privacy, etc., by its very nature are provided by the bank. However, there is a single point of failure and control, and also it is not censor resistant. The bank can cut me off the data from the database. In contrast, when we ask the same questions for the Bitcoin blockchain as a database, nobody owns it. Anybody can get a copy of it, and anybody can join the network. And this is a public database, and it is open to anybody. So the same fundamental questions are answered in a different way. Therefore, this is an ownerless database. Then how it is maintained as a database, complete and correct, is through the mining and consensus mechanism. And I think it is a brilliant innovation. I checked the Wikipedia to see what the blockchain-based databases are. So a blockchain-based database is a combination of a traditional database or a distributed database. Actually, the case of the distributed database is more challenging. Let's consider a single database that may be replicated in a Bitcoin blockchain environment. So this traditional database is augmented with multiple layers of blockchain capabilities. So that's how a blockchain database is defined in Wikipedia. And I would say that that is the commonly followed notion in practice today. And in fact, in the remainder of the talk, I will cover several such blockchain systems. So in addressing the question, can we add blockchain features to a traditional database? We can start from a traditional database and chainify it to a blockchain database. Or conversely, we start with a blockchain database and we databasify to it to a blockchain DB. In this process, I have examined several systems, and one of them was MongoDB. You all know that MongoDB is a NoSQL database system. It's a key values database system. So here is a typical Mongo database. It could be distributed or non-distributed, but could be replicated. So on the right-hand side, you see how blockchain features are added. On top of a core Mango database, there is a layer that implements the blockchain features. And this is a common methodology followed by most of the blockchain systems. In a better diagram, here we see several nodes. Each node has a core MongoDB as well as a blockchain layer on top of it. So each node is managed by an administrator, and the system is like a consortium type blockchain system. One example is ProvenDB. Please don't take that I'm endorsing or not endorsing ProvenDB. I'm just using it an example that is developed on top of MongoDB. Here is a database, and the transactions, insert, delete, updates take place. And each one of them is captured by ProvenDB, and ProvenDB keeps these change data in its own database, and also keeps the hash of these changes in a blockchain to anchor them, to ensure their security and immutability by changes by other actors. So this provides the blockchain space environment, or adding blockchain capabilities to MongoDB. Still another example is ChainifyDB. ChainifyDB inserts or adds a layer on top of a database to include blockchain capabilities. So for any table, this is for relational databases, for any table to be chainified, a digest is created. Within the digest, there are rows that includes the primary key of the change tuple, a serial number indicating the sequence of the changes, the hash of the changes, and the type of the transaction. Pictorially, this is what happens. Here is a table that will be chainified, and this is the digest for the table. Initially, it is empty, and whenever data manipulation statements are executed, a trigger captures them and allows ChainifyDB to record them in the digest. Here, primary key value 4 is updated, and clearly the update digest is recorded in the digest. So primary key value, this is the first change, this is the hash of the change data, and this is an update. Similarly, this one shows a delete. Row 3 is deleted, and a record of that event is kept here. And finally, this shows an insertion, a record of that insertion is indicated here. So it's because of the hashes, it is tamper-proof and it's immutable, and also the history of the changes, the provenance can be always can be reformed and provided to the users. Still another example is blockchain relational database that's being developed in IBM India. It's a permission setup, and it has been implemented by using PostgreSQL, and there are nodes, but the nodes are untrusted, and they implement the first ever decentralized replicated relational database system with blockchain properties, since they augment and change the code of Postgres to achieve it. What they do, they follow order, consensus, and execute, or execute and order in parallel. They follow these two strategies, And this is the block diagram of their activities. As you see, there is a client, there is a database node. The database node has a copy of the blockchain Postgres database, and there are ordering services. So the transaction is provided to the ordering service in the first alternative. They are ordered, and once the ordering phase is completed, they are executed and committed. In the execute in parallel case, they are executed in parallel. As I said, they have added many data structures to provide the database, PostgreSQL database to have blockchain capabilities. So they are able to process or build the consortium database environment. The last example I want to talk about is a completely different one. It is Credarium, blockchain-enabled Postgres. Unlike the consortium blockchain databases in earlier examples, Credarium takes a single case of centralized Postgres database and converts it into a blockchain capable database system. Here is the overall architecture of the system. There is a PostgreSQL database, and some of the tables are being chainified, are being augmented with blockchain capabilities. That is handled by the Credarium database layer, which is on top of the Postgres DB. So here is a user who wants to make an insertion, deletion, a change in the database. So the user first submits a transaction to the database, and a trigger captures this transaction and informs the Credarium database. Credarium then sends the user signed top hashes. We will see it in a moment. In other words, it gives the prior state of the database and the post state after the transaction together with their hashes to the user. The user signs that transaction, provides it to Credarium, and Credarium records it, and it becomes part of the blockchain system. Another user who wants to query the database sends a query to Credarium database. The Credarium database sends back to the user the query results with the proof. The proofs are for sure the hashes and signed signatures. However, periodically, Credarium DB also puts the hash of the blockchain in a trusted storage like Bitcoin or Ethereum. So both the user checks this trusted storage value to see it is the same that's provided by the database. In this environment, we don't see the double span problem because the application would not allow it. However, there is a similar problem called double state problem. In other words, the database administrator may take different states of the database and provide it to different users to game the system. And Credarium DB solves this double state problem with the hashes and the trusted storage. Now let's see the details of this system briefly. The Credarium DB use a tree called Merkle's tree. Merkle's tree is a combination of a Merkle tree and a radix tree. For the radix tree, the key is formed by the relation name and the row ID, or the primary key value. So the leaves, like table 1, row 1, are the leaves are the rows of the tables, and these are hashed, and they are the hashes are used to form the interior blocks. However, the common portions of the key forms the branches. That's why the structure of the tree is indicated or formed by the common parts of the key. The total key is available for the root, and then the common parts goes downward. This is a very nice data structure for representing the entire database. Now, the Cridarium DB, like any other cases, we use the transactions as state changers. A transaction takes a prior state of the database and converts it into a new state of the database. Even if there is one row changed, the new state is different than the old state. However, for most of the transactions, these changes are smaller. So the idea is to represent these states by Merkle's trees. This is the part of Merkle's tree that represents the old state of the database, and only, and this is the Merkle's tree that represents the new state of the database. Of course, only portion of this large tree will change. The remaining portions will be mostly unchanged. So when the user submits a transaction, Cridarium DB, as I mentioned, captures that transaction and sends back to the user the old hash and the new hash. The user takes these hashes and signs the transaction and sends it back to Cridarium DB. Then Cridarium DB stores them in the blockchain. Pictorially, the Cridarium DB blocks are represented here. This is the Cridarium database, and they are connected to one another by hash pointers. And each block also has a forest of Merkle's trees representing each transaction. This is a transaction, another transaction. And periodically, the hashes of these blocks are stored in the secure storage. So essentially, between the hash number 1 and between hash number 2, these blocks have been recorded in the blockchain, and if any tampering happens in these hashes, hash number 2 will be changed. So the user, both committing transactions and doing the retrievals, goes to secure storage, retrieves these hashes, and compares them with the ones provided by the database administrator to verify that there is no tampering happened and the data is correct. Actually, as I mentioned, the idea is quite different than the consortium blockchains, and bringing the blockchain features to a single centralized database. Of course, it can be extended to other environments as well. This is all I'd like to say. Thank you for your patience.
So looks like you really were so thorough. And that's going to be it for today then. So I want to say thank you, Professor. Thank you so much for joining us and putting the time and the thought into this really, really wonderful presentation. And I want to say thank you to everyone who joined us. So whether it's morning, noon, evening, wherever you are, I hope you have a great rest of your day.
Thanks, Lindsay, for giving me this opportunity to talk. And I hope to see you in Postgres conference soon in person, and the participants as well.